I'm going to talk today on using a dual switched antenna as a means of direction finding, get into some of the details behind that. Before we get started, can everybody hear me okay? Am I speaking loudly enough? Okay, good. Hopefully this is something that you find useful, and it helps you to visualize what's going on when you use a switched antenna as a means of doing direction finding. AI is great. I just described the scene that I wanted, and it came up with this, where you got a frustrated listener sitting in front of a radio, interestingly with two microphones. I don't know why AI decided two microphones was the right number. You've got somebody he's trying to listen to off in the distance, and you've got somebody else who has obviously got a rather nefarious look on his face, who's just interfering. And if you've ever been on 2 meters, you've probably heard when people decide that they don't like what somebody is saying or like the person, that they just want to create some kind of interference. Or you get a situation where somebody's maybe sitting on their microphone and they don't know that they're sitting on the microphone. And it locks up the repeater, and somebody has to go knock on their door and say, hey, actually just knocking on doors is probably enough, because then they stop sitting on their microphone, push the talk button. So I'd like to talk about how we find those folks that are, or those transmitters that are broadcasting, that we don't want them to be broadcasting or shouldn't be broadcasting. I'm going to start out, though, with a little bit of an overview of direction finding. By the way, if anybody has questions, feel free to just chime in, and if I'm not paying attention, yell at me or something like that. If you have some insight, please feel free to share it while I'm talking here, because at least some of these things, I suspect there are folks in the group here who know more than I do about it, perhaps even on the direction finding aspect of it. So, overview of direction finding and methods, which Mike just set up his Fox before the meeting, and that gave us an opportunity to home in on it on 2 meters. I want to do more than one direction finding demos. Hopefully we can do that. And what really started this, and I showed it to Steve, and he thought maybe that would be something you guys would find interesting. I put together a simulation of the 2 antennas as they're being switched, and the signals that you get at different points in the system as a result of that. So let's talk about where this started. So Mike and occasionally Ben have hosted fox hunting session before the meetings, like today. After one of the hunts, though, we were talking about how do you determine what the direction, what's the axis of direction to get you to a source. And it's like, is it north or is it south? Because there's an axis usually, and you don't know what the axis happens to be as far as is it that way or is it actually behind you? So you have to do some other method to find it, like triangulation. And I was listening to the discussion that Mike and Ben were having, and I said, I think there's a way that we can do this. I actually think it's built into the apparatus that Mike has here. I don't know how well that works as far as being able to sort out the specific direction, but we'll get to that. And I think we can do it by doing a little bit of signal processing to the received signal compared to how the antennas are being switched. Okay. So there are 3 methods that I identified as to how we can locate a signal source. One of them, of course, is signal strength. Another one is triangulation. And one more, which actually can use both of those, is transit time, as well as adding its own aspect of determining what the angle is that you want to search for the source at. Signal strength is kind of the one that everybody would think is the obvious one, right? But it turns out it doesn't work that well. Triangulation, you have to measure the angle of the source from two locations, and then you can figure out what the crossing point is. And if you use transit time, you use a detector that's sensitive to the RF phase, and from that you can determine, is it off to your right or off to your left? So let's get into this. Signal strength. We use an omnidirectional antenna, so something like this on my receiver. And to find the source, you have to choose a direction. You just start moving. And you're looking to answer the question, is the signal strength increasing or decreasing? It turns out there's a problem with that. You can actually get a lot of multipath that produces seemingly strong signals where you are standing, which may not in fact be closer to your source. But let's assume that you can get some idea by moving a great distance that, oh yeah, we're going in a direction, signal strength is changing in a particular direction. Go back there, you start over. Here's a graph of that process. You start right here at this location. Can you see my pointer on the screen okay? Right here. And you move then to this location, and you ask the question, did you change your signal strength? And you start from there, you move perpendicular to that, and you ask the question, did you change your signal strength? And from that, you might be able to actually determine where the source is located. So is your transmitter on right now? Okay. So this is an old ICOM ICR3 receiver that I'm using that has generally been pretty reliable for me. There we go. And one of the things that's kind of nice about it is it's got a controllable antenna attenuator. So if you listen to that, you can hear the two tones that are being alternated, and it gives you a sense of what the signal is. But what you really want to do is to kick in the attenuation, so you can hear. When it comes back, you can hear the receiver noise. And as you're moving about, and then it's not my, oh, okay. All right, there we had a drop. Sorry, I'm getting off camera. It's hard to tell if you're getting farther away or closer. This is really a terrible method of actually determining where it's located. But you can use it. It works okay sometimes. So there's a better method though, and that is triangulation using some kind of an antenna that has directionality to it. So Mike has his, that's a Yagi, right? Yep. Mike has his Yagi. He's used that for being able to determine the direction to your source. You can also use even a dipole for that matter. Got a dipole here. And what you're looking for in this case is ideally it's a signal strength peak. But that doesn't always work, it turns out. Turn on my attenuator again. Yeah, and that's actually good because it's telling about the performance, that this is not a great environment because there's a lot of metal in the walls, reflecting people standing around. And as you rotate this, you might be able to hear. So When you're close, it's really hard to discriminate. And this is where Mike's spectrum analyzer idea, where you get more of a quantitative sort of indication, so you can compare aspects of direction and so forth, really can shine so much better than just listening, because by nature an FM receiver.
Spectrum analyzer on that.
Yes, exactly. Yeah. By nature, an FM receiver has a limiter in it, right? And that limiter tends to saturate you, so you have to kind of find the edge of performance when you're dialing your antenna around. Something like that way, maybe. It's hard to tell. So that's not a great technique either. Yes, sir.
Could you use the null instead of the peak?
Yes, you can do that, but I wasn't picking up on a null with this antenna. If this were a Yagi, though, you would have a better chance of picking up on where the peak happens to be, but you get all the side lobes usually where you do get nulls, and those can be a little confusing, but it'll certainly give you a better indication of direction, and you can use that angle that you've determined then to do a triangulation technique, where you either make a first measurement and then move to a new location, make a second measurement, or you can have two people or more that are coordinating their directions, and from that you can, for longer ranges, then you can figure out more quickly where a interference source happens to be coming from. Did I answer your question? Turns out there's still a better method than this, and that is using transit time or phase as a means of discriminating the direction of your signal source. And I'm going to use Mike's equipment here. So what he has is there are two dipole antennas, a first dipole, a second dipole. They join together here, run over to a switching box, which is right here, and it chooses this antenna and not that one, or this antenna and not that one. And it's chopping between the two. So it's a pretty straightforward method of just flipping between the antennas, but it gives you a measurement that is very interesting compared to the other two techniques. So let me turn this on. What you're going to hear, you'll hear the transmit. Did you have something, sir? No, okay. You'll hear the audio from the transmitter, of course, with the modulation and so forth on it. But in addition to that, you will hear this thing switching between the antennas. When it's face on, there will be phased, the signal from that transmitter will be phased identically between the two antennas. And you won't hear any artifact from switching. If you're off axis like this, you will hear a phase, or the artifact of shifting that phase. And I'll get to the details here in a little bit. But I just wanted to show you what this looks like and what this sounds like. So if I turn on the radio, okay. Can you hear that? Okay. All right. So just remember that sound. We're going to superimpose on top of this a very high pitch, which is the switching that goes on between the two antennas. Okay, I'm going to wait for it to cycle through. Can you catch that? Yep. Okay, now. Oh yeah. All right, you hear that high-pitched tone? that's the sound from switching between the two antennas. The louder it is, that tells you that it's off of one of these axes. As you get this face on, that pitch will go away. Not now, of course. There we go. Right about there is what I would guess, and lo and behold, it's right on foresight. Now we do have a lot of reflections in here, but this has a much better chance of getting the signal.
This is a really impossible environment.
It's very difficult, you're right. But you can tell, we're getting a low signal, like right about here. Right, that high pitch. So, that's the idea. Yes, sir.
Got a question, does it switch back and forth between the two antennas at a predetermined rate? and
Yes.
Do it constantly?
Yes.
Or I was gonna say, or does it only switch when it notices that the other one is picking up the signal better?
The first, what you described, which is, so at about 1,000 times a second, we're choosing one antenna versus the other antenna.
Right.
Okay? So let's talk about this a little bit. There we go. And of course, the method is better, arguably, because you know what the axis is that you're tracing, but you still have to do a little bit of triangulation sometimes because you don't know, is it back that way or is it over that way? You actually have to make a movement like I did a moment ago to say, aha, it's over there. All right. So you got a guy, he's got his radio direction finder with the two antennas like I did a moment ago. This guy, this is AI again, by the way, that drew this for me.
Really?
Yeah.
Well, how much description did you have to put in there?
So I went to Gemini, which is gemini.google.com, and I typed in something like middle-aged man walking in the field with a radio direction finding unit.
You got that?
And I got that.
Wow.
Yeah. And it shows the RF signal source, and it puts some nice trees and clouds behind it, so it's a nice day. It's pretty good. And I didn't pick up on, he's got the right number of fingers on his hands. And things are pointed out a little bit funny. Headphones are good. Switched antenna DF unit is pointing to the antennas. No, it's really the box, but it's pretty good. So if you ever need to have like a line drawing of something, oh, I said line drawing. That was the other piece of it.
Oh, yeah.
Anyway, it produces a nice little image like this. And then I also said, show me a top view. It turns out I had to do some hand editing on this one because it doesn't understand a figure 8 pattern. It actually gave me a cloverleaf pattern, so anyway, I had to clean that up a little bit. But you can see that there are going to be two deep nulls on this, which you kind of got a sense of that when I was wandering around, right? That right on the bore site, you don't get much in terms of that whining pitch coming through, either on this side or on the opposite side. But off either side of the antenna, you do get some pretty strong signal pickup. And you can use this as a means, just like we did with other types of directional antennas, using triangulation as a means of determining source. But the good thing about a null is it tends to be a very sharp indication. Either side of it, you have signal, but it's within a few degrees. If you look at a Yagi, you're talking like 10, 20 degree beam width. That it's a pretty strong signal that without like a spectrum analyzer to indicate signal strength, it's hard to actually get the idea of where exactly you should be pointing. So, kind of did the demo of the two directions already, so I'm not going to focus on that. So what are we hearing? This is what I described earlier. So you've got a signal source up on top. You've got a field that is washing downward in this screen, and you've got two antennas that are indicated. One antenna is here, the other antenna is here. Those signals are then going to an RF switch that is being switched at an audio frequency, and that goes into a standard FM radio. And the output of that goes to a speaker, which you were able to then hear the pitch. And as you're on bore site, you get a minimum amount of the signal at the frequency of your audio frequency oscillator. If you're off, you get a pitch that is stronger. And so a couple of meetings ago, Mike had brought in his scope, and we put a scope on the audio signal to actually see what comes out of the audio jack on a radio. And Harry, you were interested in what that looks like. Well, this is what the signal looks like. It's almost a triangle wave. It does have some other wiggles and ripples in the waveform, but that's the signature that you are going to see. It goes up, it comes back down to a negative value, and strokes up again. It's pretty close to a triangle wave. Why does it look like a triangle wave? Well, we'll get into this in just a minute. Once you look at what the signal processing looks like in an FM radio. So you probably all know this, but bear with me while I cover it. The block diagram for an FM radio is something roughly like this. You've got your RF input from an antenna or the switching network or whatever it is that you're applying the signal to, an RF amplifier or a preamplifier. There's a mixer along with a local oscillator that takes you down to maybe 10.7 megahertz. It's a pretty common IF frequency, and much of your gain in the system actually then comes from IF amplification. And people do that because they know what the frequency is, and they can lock in on circuitry that's optimized for tuning that particular frequency and band limiting that. Because this is FM, you don't care about, in fact, you want to remove the AM component. So typically you have some sort of an amplitude limiter. Most circuits will do this with a couple of parallel opposed diodes or some simple sort of a limiting circuit like that. And then you feed that into an FM discriminator. So what's an FM discriminator? What it does is it gives you an output, the raw output of the FM, not the filtered output after the amplifiers, audio amplifiers, but the raw output that comes from an FM discriminator is a voltage that's related to the frequency given to it compared to what it's expecting. So if 10.7 megahertz is its expected input, you'll get, say, 0 volts coming out of this discriminator. If you're high in frequency, say 10 kilohertz high, so would it be 10.71 megahertz, you'll get, say, a volt coming out of the discriminator. If you're at 10.69 megahertz, so 10 kilohertz low, you'll get -1 volts coming out of it. So the output actually tracks with the frequency of the incoming signal. If it's high, your output of your discriminator is high. If it's slightly low, but lower than your expected frequency, the discriminator output is low in frequency. We're not actually just detecting, though, FM, and that has an interesting consequence, and I'll talk about that in a second here. But the output of the discriminator typically goes then to an audio amplifier that has either some low pass or some band pass filtering on it. Most radios, like my ICOM, wherever I put it, is, oh, here it is. This is, it's probably, communications bandwidth like 200 hertz to 3 kilohertz or 2 kilohertz or so, to just emphasize the intelligence that's part of the transmitted waveform. And then that, of course, is delivered to a speaker. So far, so good, by the way? Okay, good. So when we use this type of a switching of the antennas, something interesting happens in an FM radio. If you are on bore site, or you got two antennas that are aligned so they're same distance from your transmitter, so it's bore site with your transmitter. You can't tell, there's no RF phase shift when you flip between the two antennas. So there's just a single frequency coming into the radio. And this top diagram that's what the intent is to illustrate. Even if you're switching between antennas, exactly in the middle of that diagram, as far as the radio is concerned, it's not hearing any phase shift. There's no shifting going on. If, however, you're off axis, in this case, I'm showing 45 degrees off axis, before the shift occurs, you have one phase of received signal being delivered to the radio. You then shift and suddenly get a phase shift. And then you go back to that same exact frequency. So the frequency, stand up. The frequency here is your carrier frequency. Let's say it's 146.56, I think you were at. The frequency here, 146.56. The information that when something happened is this. It's that shift in phase. So it turns out when you do a phase shift, there is a frequency component to that. And this is what the discriminator produces as an output. It produces impulses every time you get a phase shift. And those impulses, when they are passed through the audio stage, the bandpass of an audio stage, produces a signal that looks kind of like what we saw earlier, sort of like a triangle wave. Now, I didn't try to tune this exactly like Mike's radio receiver was set to as far as bandpass, with all the poles and so forth at different frequencies, but this is pretty close to that triangle wave. So I actually want to change to another computer where I did a simulation of this process. 1 second.
Need a cable stretcher.
Yeah. There it is. Gotta flip it over.
Oh, that helps too. Otherwise you get an inverted image.
Right. Yes. All right. So, there we go. So this is what you just saw. I captured waveforms from this. The program that I like to use is LabVIEW for doing my simulations. It's LabVIEW turns out is it's a graphical programming language. It's very much like a schematic, and it allows you to work with these large functional blocks and kind of piece them together like a block diagram almost. And so I put together a simulation of what the phasing looks like as you shift from as you shift the phase angle. So I'm gonna adjust the phase angle here. So sorry, what you're seeing, top graph. This is the top graph is the sine wave with a phase shift applied. The bottom is the discriminator output that the receiver would be seeing. So right now, There's no discriminator output. The output voltage, say, is 0 volts. And that's because we're not seeing any kind of discontinuity in that received RF signal. So as I introduce a little bit of a phase shift, so here is 10 degrees, 20 degrees, 30 degrees, and we keep going. You can see that spike that's appearing right here. That is the discriminator output. It's a little spike that happens to occur at the output due to the frequency change.
So what did you do to get that?
Yeah. What are you in or using as a viewing program?
So this is LabVIEW. You don't know LabVIEW.
But
Okay.
Okay.
what are you doing when you change your sine wave? What did you do to cause that change, and what is the change?
So the change is that we are taking two sine waves, one that is before the switching point and one that is after the switching point, and I'm moving them together. So there's this discontinuity that occurs right here. And that produces on your discriminator a spike right here. And so this goes positive, why? Because we're actually advancing the phase rapidly. If I move this back and I go the other direction where I'm actually delaying the follow-on waveform, you get a negative output. Okay? Now,
So is that an audio signal?
this particular one, this is not an audio signal. It would represent an audio signal. I'll get to the detail here in a moment, though. You go.
The sine wave on the left half of the top figure is from antenna 1, and the wave on the right is from antenna 2.
Correct. Yes, exactly. Right. Good point. Yes. This would be from antenna 1. This is the RF signal, by the way. This is the switch point where you flip from one antenna to another. And this is the other antenna's RF signal, received RF signal that you're delivering to the radio. So you're actually getting phase modulation. And you're getting, because it's square wave phase modulation, you're getting a rapid shift in phase that translates into frequency content that the FM radio can receive.
So is this the signal that's going into the radio?
Correct.
Okay.
And I'm only showing one transition.
Yeah.
As you go from one antenna to the next. If you look carefully on the left, you can see there is the opposite polarity. I just don't have it pulled out. But this would be when you're switching back to the first antenna. Okay? And of course, the maximum is right there at 180 degree phase shift, and that's your maximum discriminator signal. Interestingly, if your antennas are more than a half wavelength apart, you'll actually, when you're broadside or end fire toward your source, it'll actually have a reduction in signal. In fact, if they're a wavelength apart, you'll actually have a null forward, you'll have a null to the side, you'll have a null in the back, and you'll have another null on the other side. So it goes to like a clover leaf sort of a sensitivity pattern. Most people don't do that, though, because it introduces uncertainty. Okay? So this is the signal, though, right here on this lower plot. Those are the spikes that I had on that previous plot. Okay? So you get a little spike every time you switch from one antenna to the next. Good? So we go back to this. So this works. Ta-da. Pause this. Okay. So that's what I was trying to demonstrate, was the positive spike here. You pass this through the audio stage, which has a band pass to it, and you get this sort of a signal. Okay. Now we finally reach the point where Ben and Mike and I were talking in the parking lot after a fox hunting session, and the discussion was, is there a way to determine the direction? So is it this way or is it that way? And it turns out there is, and it lets us follow the beam in without any triangulation. It gives us a determinate direction, and it gives us a sharp null with weak signals, strong signals. You can even use stubby little short antennas. You don't need to have them be true dipoles, quarter wave dipoles. As long as you can hear a signal and you can create that phase difference between them, or time difference between the two antennas, you can determine where the axis is your signal's coming from. So we kind of covered this a little bit. What happens when we switch at an audio rate? So when your antennas are facing your source, you get no net phase shift, and so you don't actually hear the pitch of the antennas being commutated back and forth. If you go on an axis where there's an offset to them, that's when you'll hear the signal, and that's how you can actually use that information to determine what direction your source is. So I'm going to go back now to my other computer. This is the simulation that I did for. Is it up? Good. This is a simulation that I did of the wave front. So I'm going to turn it on. Hopefully it's working. Yeah, it's working. Excellent. So signal source up here. Waves are traveling down. You can see that, right? You guys can see that? Good. And you see we're switching between the two antennas periodically, and we can rotate the antenna like this, okay, so that we can simulate one antenna encountering that wavefront before the other one, okay? And the other thing I added to the simulation was a means of monitoring the signal. So I simulated the what these signals are going to sound like, and hopefully you can hear them. I'm going to move the microphone over here because it might get a little loud for that. There are actually two things that are working in the simulation. One of them is this graphic, which is, admittedly, it's a cartoon of, the RF wavefront where it's traveling at the speed of light, not, 1 cycle per second like is being shown here. And we're switching between the two antennas much, much more slowly than what I'm showing here relatively. So if I enable my detector, this red waveform, yes, I think you can see that, right? The red waveform, that is the signal that's driving the two antennas to be switched, and so when you're down here, you are on one of the antennas. When you're up here, you're on the other antenna. So this is exactly what Mike has on his equipment. So right.
How do you distinguish the antennas that it's coming from?
So there's an RF switch that is controlled by the red waveform. So here, here you're on one of these waveforms.
Oh.
When you're up here, you're on the other one.
Okay.
Okay. And as we rotate the antenna, so I'm going to go 10 degrees. So there is the audio signal that you would be getting out of your radio. I don't know if you can hear that.
I'm actually making noise.
Yeah. And the further that you rotate the antenna, the bigger the signal out of your radio speaker becomes. Now there's something really interesting that happens. When we have rotated the antennas like this, you see that the radio audio output is positive when we're on this antenna, and it's negative when we're on this antenna. If we go the opposite direction, you can see that we now have them phased identically. We can actually use that information
Oh,
to determine
direction.
the direction. Exactly. Is it off to the left or is it off to the right? And in fact, the way you do this is by, I'm going to take this down because it's kind of irritating. The way you do this is you simply multiply the two signals together. You multiply the red signal times the received blue signal. Green, sorry. I'm still learning my colors.
Cyan.
And so if you have a -1, for example, times this, negative times a negative number is a positive number. A positive number times a positive number is a positive number, right? If we flip this the other way, positive times negative is negative. Negative times positive is negative. And you can filter that signal out, and that's that blue straight line that you can see right there that keeps increasing in value as we progressively rotate our antennas. And you can use that to drive an indicator like this, or you can go the other direction with it. Oh, went too far. Now, there's another aspect of this process. So, actually, let me step back for a minute. Just repeat what I've done so far. I'll come back to this in a moment. So, this is what you saw previously, right? Which is, it's just an audio pitch that you're hearing. You have the two antennas. They're at different points in the wavefront. They're fed to an RF switch. You're flipping the switch at an audio rate, a kilohertz or so. That goes into your FM radio. It turns each of those phase detections into a spike. Audio filtering then turns that into something that's kind of like a triangle wave. For detecting the direction, we've added this. We've taken the output from the driving signal from the audio frequency square wave generator that flips the switch. We turn that into a ±1 signal. You multiply it literally, it's kind of like on your scope. You know how you have two waveforms? You flip the add function or the subtract function on your scope, and it just adds it kind of instantaneously together. This is the same thing, except instead of adding them together, you're just multiplying them by each other. So it is a multiply operation. So you take the audio from your radio, multiply it by ±1, you send it into a low-pass filter, you get the blue line, that nice flat blue line. The narrower that filter is, the smoother that line is, so that interference like people talking or CW, audio CW, it's ignored. It just goes away from the signal analysis because it's so far out of band. This technique, by the way, is it results in filters that are like a hertz wide at that 1 kilohertz frequency, and then you have an indicator as a result at the end of it. And so I guess I got to my conclusion faster than I thought I was going to. So anyway, we can use this technique. It turns out we can still use signal strength. We can still use triangulation, but you can essentially, from a stationary location, you can determine the direction that a source is located in. Now I want to come back because there's something else I wanted to tell you guys. Multipliers. Let me talk for a moment about multipliers. The symbol typically in a block diagram, schematic block diagram, a mixer is shown like this. You'll notice that X on there, that's a multiply operation. So you're taking one signal times another signal, you get an output. It's got the sum frequency products, it has the difference frequency products in it. Not suitable for multiplication, at least 4-quadrant multiplication. 4-quadrant meaning both inputs can be either positive or negative. Is a single balance mixer. You can use a double balance mixer, but it doesn't go down to DC. This relies upon going all the way down to DC. Why doesn't this work? Because you get a transform in the output. So you could do something like this, where you put a differential amplifier on the output, and that gives you the signal that is good down to DC. You can use a triple balance mixer. It's just excessive complexity, though. And typically in circuits, the way that you do multiplication is a 4-quadrant mixer, particularly of the style called a Gilbert cell mixer, where you've got 2 transistors on the bottom that each feed into what look like differential stages, and then the differential stages are cross-coupled on the top. And I think I didn't do a switch equivalent to that. But you are switching between this differential stage and that differential stage, and then you cross-couple, and the net effect is you're multiplying 2 signals together, and it's a legitimate 4-quadrant mixer. So I think there was. So I can go back here, and there it goes. Oh, that's where it was. One of the things I can also do is I thought, how good does this work in the presence of noise? So if you look at, because you're going to be fringe area at some point, right, where you're going to get noise. So just watch what the indicator does over here, and then you can also watch what the signal looks like. So I'm going to increase my noise. So you may not be able to hear it yet, but you can see it on the screen. There's a little bit of noise there. There. So you can really punch up the noise level. Yeah, you can really punch up the noise level. And if you look, you're really not seeing a deviation of any significance on this meter. It's still indicating 0. If I turn my antenna, though, here's 10 degrees. Can you hear the pitch and the signal out of the speakers? Yeah, a little bit, not much, but we're getting a really solid detection. So there's 40 degrees of offset. I challenge you to look at this signal, the green signal, and say, oh yeah, I can see that signal in there. Here, let me take it down so you can see what this is looking like. There. That's the signal that's buried in the noise. So you're talking about a signal-to-noise ratio of 0 dB. And you're able to...
But if you're filtering for that frequency, you should be able to eliminate the noise then, shouldn't you?
Yeah. So you can add...
And these are audio frequencies.
These are audio frequency. So you can add noise to it, you can add voice to it. Doesn't care, it just keeps on working. So that is it. That's what I had to talk about. Thank you.